Still not used to it. Thank you, though. Appreciate it.
Do you want me to stay or are you
As long as it's going, I think it's okay. And then I go back and stop the broadcast at the end. I can trim it later. Right?
Yeah.
Thanks, James. Appreciate it.
Like protesting, like.
How did like did they like sample people?
It's just either all one or all wrong. Anyways, thank you. Appreciate it. Thanks.
Did you guys have a original concentration as well, or did you actually get good? Yeah, we're just
You guys are big
Still right.
What?
Oh, we didn't even okay, so do you so we can hope for
You're a bit too. Much God is a de-staining solution. If your concentration is too low, it's going to increase the concentration.
And they're literally like, oh, we're gonna grade you on this concept. Everybody shares the same set box.
So I'll give you like a girl's shower. I got my thing.
I know I lied.
And it's good. I don't think I think it's
Just don't get
Are you starting at
2:10?
okay? And you're already set up. That makes my life very easy.
I guess so. Do you know at what point the internet will become active? Because right now we're doing it wirelessly through the Wi-Fi system.
I think at this point, yeah, there haven't been any network drops put down, which is why this account doesn't do anything yet. I haven't heard a time when it can actually happen. Hopefully sooner than later, but I imagine it has to go Wi-Fi for
In theory, we're trying to stream this, and we're not sure if it's going to go through Wi-Fi or a lot of it depends on what's going on here and how much signal it has. Getting here, it's not bad.
Sure. Yeah, that definitely makes things interesting. I've never had a problem with the before, but it's so hard.
It was a little slow because we were trying to set up a Google Hangouts on air to stream it over YouTube. Just connecting to the Hangouts on air took a little longer than we did. So we'll see how it goes. In theory, this will be really choppy. Let's see.
Yeah, as long as I assume once you connect it should stay stable unless you make major changes, but in the world of internet, it's always so hard to tell. I think that the person who best have the answer is the one. They should have an idea as to what but I imagine it shouldn't be more than 6 weeks.
Okay, fair enough.
Don't take my word for it.
Okay.
And have a good night.
See you. Thanks. So if I record the lecture too?
We should just share it like on
What time do you have? Slightly. Apparently, there's issues with. Oh, there's like a note. Okay. I guess they want the note in, yeah, it'd be great if you guys could set up the internet. I know it's not. Did you try? We did. It's on live. Yeah. Oh, really? Okay.
Because I think the internet is supposed to come directly from the wall, it should come from the closet. Because a lot of the other systems had supposed to control it. That didn't. But I guess it's not my system. Okay. But you're good to go.
Okay, folks, if you don't mind. Unfortunately, I heard that this isn't the best room to actually do lectures in because there's a lot of rebound off the walls of audio and things like that. So I'm going to try to get started, if you don't mind. We have a really lot to cover today in today's lecture, and it's basic physiology. It's somewhat of a review, but you'll need to know a little bit more detail than what you've learned previously in physiology. So if you are interested in chatting about any of the material at any point in time, whether it's today's lecture or down the road, feel free to email me. My email address, the best contact is there for you at Gmail. I'm more than happy to talk to you about anything related to the course or anything related to neurophysiology. Just out of curiosity, have any of you in any of your labs or as a research project actually recorded from cells, like you've done electrophysiology or neurophysiology at all? Okay, so one of you, 372, a little bit. I don't know. I have no idea. That's why I'm asking. So a lot of you will be wondering why do we have to actually learn how to do all of the classic neurophysiology? Do you actually use classic neurophysiology the way that it was put out in the 1950s and 1960s? And the simple answer is yes, we do. We still use classic neurophysiology. I'll take you through it and I'll tell you the reasons why we still study it. You don't have these in your notes and it's okay. You're not going to be tested on any of this. It's to put things into context for you. Why are we studying classic neurophysiology, basic membrane properties first, and then moving our way into different systems? So the human brain is actually an incredibly well-organized organ that allows a lot of different types of behaviors to occur. Overall, somewhere between 10 synapses to about 10,000 synapses occur between individual neurons. We think we have somewhere between 80 to 100 billion neurons in the brain. It's hard to count them, as you can imagine, but all of this is related to what we're going to be covering in the next series of lectures. Because when it gets to the brain, we can actually understand when the brain is working well, the individual neuronal connections. When they're working well, we have appropriate behavior. When they're not working well, we have two different issues. One is a neurological issue, and one becomes a psychiatric issue. And throughout this course in neurophysiology, we're going to be examining both. And in fact, it's a little bit misleading because you think that there's this clean divide between neurology and psychiatry. And in fact, it doesn't tend to work that way at all. And we know now that when the brain is not working well, that there is this false dichotomy that has existed between the brain and the mind. In fact, we can't really define the mind really well right now in 2015. We have no idea, for example, how this organized structure of 100 billion neurons actually produces what we call the mind. Is it a philosophical construct? Is it a biological construct? It's really hard to say. However, if we go back to first concepts, when the founders of modern medicine decided to separate out the problems that we have in the brain related to neurology, the physical part of the brain versus the mind psychiatry, when that occurred in the 19th century, it was a clean divide. They thought it was one was organic, the other one was not. And it turns out that many neurological illnesses, things that are associated with classic neurology like Parkinson's disease, also manifests itself as a psychiatric disorder as well. And we'll get into that when we talk a little bit about schizophrenia, as well as with Parkinson's disease later on. So this dichotomy is something that we'll be going back and taking a look at as well. We can also learn a lot, and this is more of a cognitive process or a reverse engineering process, where you can look at specific brain diseases in specific regions of the brain and figure out what it's normally used for. And we'll see that, especially when we get into metabotrophic receptors, when we start looking at narcolepsy, and one of the best studied neurophysiological phenomena that relate to a brain disease process. When we get into narcolepsy, you'll understand how we went about looking at narcolepsy from a lack of specific receptors. So throughout this course and throughout this section of the course, we're going to do a number of different things. One is we're going to start with looking at the cellular basis for communication, how neurons communicate. And some of that's going to be a review. Some of it's going to be more detailed than what you had in your third year. We'll eventually start next week to get into how different neurotransmitters and different neuromodulators work. We think as of 2015, there are no new neurotransmitters out there. However, we are finding new neuromodulators. They don't work in the classic neurotransmitter pathway. We think that we are still missing a few neuromodulators, and we'll get into that a little bit later on. All of this is really to allow you to understand the proper functioning of the nervous system throughout different regions in the brain. And we'll take a look using the same principles throughout the rest of this course in terms of major psychiatric conditions like schizophrenia, as well as neurological illnesses like Parkinson's disease, and some other ones as well that kind of bridge the two or span the two, things like narcolepsy and other sleep disorders. So we're going to start at the very beginning. We need to understand how the basic unit of the brain, those 100 billion cells, specialized cells in your brain, how it works. And I know that you've all taken PSL, and it sounded like from the conversation that you guys were having before class started, you guys are all experts in physiology, yes? Yes, okay, perfect, good. I'm glad to hear that. So we're going to go back and revisit the ionic basis for the membrane potential. I'm not going to be testing you on the sort of bare basics, like what parts of the cell. I need you to pay particular attention to things like the reversal potential, and we'll go through that today. How we derive things like the Goldman equation, those types of things are what I'll be testing from this particular lecture, but I wanted to give you some context for everything as we go along. Some of this will also make a lot more sense when you have the tutorial where you'll actually use computer simulations to model some of what we're talking about, not this Friday, but the following Friday in tutorial, and I'll also be there in tutorial with you. So if this is one of those 100 billion cells that we have in the brain, or somewhere between 80 and 100 billion cells that we have in the brain that allow us to do all sorts of different things, and when they go wrong, produce neurological or psychiatric conditions, the integrating center, as you probably know, is the cell body along with the dendrites. These are where the synapses are going to be making their connections. Somewhere between 10 for some cells, all the way up to 10,000 for other cells. The dendrites are where the majority of the integration takes place, and all of that, again, making its way down into the cell body. But we're going to take a look at the very basics of how different cells, like neurons, actually produce changes in voltage. And so we'll start off by going back to really basic cell biology. So all neurons are enclosed by this phospholipid bilayer, and this membrane that you see here makes things really interesting. There's an outer environment that we can measure, and we can manipulate the outer environment really easily. Some of you will do that in labs where you, by simply changing the ionic composition of things out here, you can directly affect what goes on inside the cell depending on properties associated with this biophysical membrane. This membrane by itself, if it's nothing else, it represents sort of a plastic bag. You can't get things into and out of it. It's impermeable by itself. It's impermeable to charged solutes, which means ions, in other words, unless it has specialized proteins embedded within it. Again, hopefully all review for you. So how do we start manipulating some of these differences in ionic concentration? So we have an extracellular environment out here, and we have an intracellular environment in here. Are the two identical? It turns out that they're not. And part of this is because we have embedded within this phospholipid bilayer, we have these membrane spanning proteins that goes across the entire membrane from one side all the way to the other that allow for the exchange of different types of ions. And these transporters are what create these concentration differences, or these concentration gradients between the outside environment as well as the inside environment. As you all will probably remember, these transporters involve active transport requiring ATP. They need ATP to cause the transport of things like sodium as well as potassium. Some of you will also know this by a different name, like an electrogenic pump or an electronic pump. Do you guys remember the sodium-potassium ATPase? How many sodiums are transported out? How many transported in? Potassium's in. 3 to 2. Great. So you are a really good class. Great. Glad to know that. So these membrane spanning transporters are really important. In addition to that, we don't only have these transporters to set up these electrochemical gradients, we also have these ion channels. These ion channels are where we're going to spend a lot of time over the next week and a half or so to get you familiarized with how do we actually go about investigating and interrogating a neuron to see what properties it actually has. If someone were to just give you a neuron, how would you know like what the neuron actually did? What kind of neurotransmitters were responsible for causing it to fire, etc. All of this is important in terms of the basic physiology that we'll be talking about right now. These ion channels are also proteins, and I'll show you this on the next diagram. And these channels are also important in the sense that they have a pore. They have a central domain that allows communication from the outside environment, the extracellular, to the intracellular environment. These are things that allow for charged ions. Because the membrane is impermeable, it allows these charged ions to traverse this lipid bilayer. They allow things to move across this lipid bilayer, in other words. It's a shortcut mechanism that's been built in. They are, for the most part, selective. It's not just a random opening and closing that allows any ions to go through. The different channels have some selectivity based on the size of the ions as well as the charge associated with them. Some ions are cationic, positively charged, and some are anionic or negatively charged. Some are divalent, like calcium, where you have 2 charges versus having monovalent ions. And this selectivity is all at the level of the pore. In addition, some of these channels that we'll talk about much later on, and some of you will remember this from your 3rd year physiology, some channels also possess at least one gate that regulates the opening and closing of these channels. They're not open all the time, in other words. You guys remember any of those gated channels? What's the most classic gated channel that you remember? So the voltage gated sodium channel, right? Which has both an activation as well as an inactivation gate, which regulates the channel opening as well as closing. So if this was an example of a typical channel, this would represent the pore region that allows for different ions to move across this impermeant bilayer. So ions can't cross here, but they can cross through this open pore. And they do so via diffusion. It's a simple diffusion process and involves diffusion down their concentration gradients. So here in this case, it's a potassium channel, so it's selective for potassium, even though there are a number of other cations as well as anions out here, it's selective for potassium. And because it's moving down its concentration gradient, you'll see that the arrow moving it down its concentration gradient is much bigger than the arrow allowing for influx inwards against the concentration gradient. So a couple of other really important concepts. And again, I don't know how much theoretical physiology you've had. Some of you will have taken different labs. You tend to have this misrepresentation in most of your 3rd year physiology textbooks, and in fact, in most of your physiology textbooks, that you get this massive bulk movement of ions through these channels. In fact, it doesn't turn out to be the case at all. So these potassium ions can leave the neuron through these open potassium channels, but there are also these negatively charged large molecules. They never leave the cell unless there's damage to the membrane itself. And these large negatively charged molecules, like proteins, really large proteins, as well as RNA molecules, help to maintain this overall gradient. So overall, if this channel is open, this potassium can leave, but it can't leave completely. There's this separation of charge that starts to develop as this pore opens up, but the inside of the neuron eventually becomes more negative compared to the outer part of the neuron, even though there's because of this local buildup of negative charge. You have net movement of potassium out, which means that locally inside this little microdomain, you'll have a net negative charge because of the loss of the positive charges down the concentration gradient. Eventually, around these microdomains, you will still have the, you will eventually reach equilibrium, at which point there'll be no net movement. You'll still have ions moving in and out, but no net movement. So if you go back to your physiology textbooks, this phrase would not ever be found there. It's not a microdomain. They're just looking at the overall bulk movement. But in fact, inside the cell, as a whole, the potassium levels are still high inside the cell just because this potassium channel is open. But this local area here, in fact, has changed and is now equilibrated. And this again gets into the concept of a microdomain associated with these channels. So this gets into this idea, well, why does it actually reach equilibrium? And why is this equilibrium potential, why is this equilibrium value so important? Because at some point in time, there's going to be no net movement of those potassium ions. They'll still be moving, but there will be no net movement of charge. Some might be going in, but an equal number will be going out. And when this exact balance occurs, it occurs because there is no more of a concentration gradient, and it's exactly balanced by this electrical gradient. Remember that electrical gradient being set up by those anions, as well as those microdomains that we just talked about. So this concentration gradient is important. It's set up initially by that transporter system, and it moves things down this concentration gradient that was originally set up. And then eventually, as these microdomains, as these channels open, at these domains, we will have these opposing electrical gradients that set up this equilibration so that there is no net flow of these ions. You guys have any questions so far? No? Yes? The overall size of the microdomain? A lot of it has to do with the internal flow dynamics inside the cell. There isn't a lot of movement or microfluidic movement. And so because these are in an aqueous environment, it tends to be somewhat limited. It tends to be within a very narrow area around the channel pore itself. Doesn't spread out very far. So a couple of other things. Again, you kind of have this really misleading view of what ion movement looks like. The total number of ions that actually have to move in order to produce these types of changes, to cause these changes in electrical potential, is actually very, very small. It's about 10 to the minus 12 moles, for example, of potassium per square centimeter. Centimeters being a massive unit relative to the number of moles. In fact, in neuron itself, do you guys have any sense as to the size of a neuron? If I look at just a neuronal cell body, how big is a neuronal cell body? Is it a centimeter? Probably not. Any guesses? A micrometer? 2 or 3 micrometers? Nanometer? Any other guesses? So on average, it's about 100 microns or 100 micrometers. So we're talking per square centimeter, we're talking a very small number. And again, we have to scale this down. So we're not talking about this massive influx in and out of these ions, and we're also talking about these microdomains. So that is one of the reasons why the concentration of these permeant ions, why don't you get this massive change outside the cell? Overall, you don't, right? If you're doing recording, as I asked earlier on, you're never going to see the overall bath recording solution drop in terms of the concentration. It's only at a very small level. So the concentration of the permeant ions outside and inside really don't change that much. You have this idea that they do, but it's only in those little microdomains that we are talking about. It's in this restricted vicinity of the pores. So if nothing else, you should remember that it is a very localized phenomenon. Locally, we'll have this equilibration, but in terms of the overall intracellular to extracellular, that stays pretty constant. And when we're talking about these equilibration experiments in the next few slides, it's really at the level of these microdomains. Just again, to give you an idea and some perspective on this, you don't need to memorize any of these. Hopefully by the time you get into the tutorials, it will be second nature. I'm not going to be asking you for definitions related to current or anything else. It's just to put things into a frame of reference for you. So when we talk about electric current, we're talking about the net movement or the flow of an electric charge. And we measure this in amperes. You'll always see current related to amperes. If you see amperes, you're talking about the movement of ions. In neurons, usually for a positive ion or a negative ion like chloride, when this moves across, we're talking about a really small current that is being generated. The net movement across, every single ion channel is open in a particular neuron or patch of membrane, you would only be looking at about 200 picoamperes, a very, very small number. We still measure that, by the way, in electrophysiology. But in order to be able to measure this really, really small amperage or this current, we actually have to be able to use an amplifier of several different magnitudes of orders. So we have to be able to amplify the signal in order to be able to measure this in electrophysiological experiments. So again, just to put things in perspective, when you're looking at the net movement of electron flow down a copper wire, for example, you're looking at 15 amps. And that, if you were to touch 15 amps, that would hurt. If you were to touch a neuron, of course, it wouldn't, because the amperage is much lower. Another useful term to make note of is voltage. We'll need to know both of these, both the current as well as voltage, or the IV relationship, in a few moments, because that is something you'll need to know for your midterm exam. And this electrical voltage represents the electrical force that would drive that movement of ions between two different points, inside the membrane to outside the membrane, or outside the membrane to inside the membrane, representing those 2 points. And we measure this as volts. Again, it's typically referred to in your third-year class as the potential difference, the difference that would allow for ions to flow into across a particular membrane. In neurons, this difference, this potential difference, is typically referenced as about minus 65 millivolts. You guys have all learned that in your third-year physiology, right? Okay, so and this is millivolts, 1,000th of a volt, and the household power outlets that you measure here are typically about 110 to 120 volts, so much, much bigger in terms of our ability to measure this. So a couple of other conventions, and this will become important when we get into the IV curves that you're going to have to know in some more detail. When we talk about voltage, across a neuronal cell membrane, we measure it from the inside relative to the outside of the neuron. And that will become really important, not this Friday, but in next Friday's tutorial, where you'll again be reintroduced to the way in which we measure voltage. We measure from relative to the inside of the neuron. When we talk about current, we're always talking about the movement of positive charge. We put it in relation to positive charges flowing in one direction or the others. So this will become a little bit more clear when we go through the IV curve for the chloride ion at the very end of today's lecture. So if we know, and we can actually go back and manipulate the concentration gradient for an ion, we can control the outside environment, for example, and we can also sample the intracellular environment. We can go and calculate this electrical gradient that allows no net flow of these ions. We can manipulate the systems to allow us to get this electrical gradient, which allows us to determine when no net flow of ions actually occurs. When this occurs, though, what we say is that this is the ion's equilibrium potential, or the E ion. So for example, it could be E potassium. Another way to take a look at this is if there's no net flow, there's no current, one of the things that we say is going on, the equilibrium potential for that ion represents the reversal potential for that ion. And graphically, in the next series of slides, I'll show you what this reversal potential refers to. Is that new for any of you at all? Like, you've never heard of the reversal potential? Okay, so I want you to keep clear that the equilibrium potential, which represents no net flow of ions, there's no current, in other words, there's no net movement, no current, 0 amperage, or no current, is also exactly the same as the reversal potential. So being able to calculate this becomes really important. And I'll show you why we call it the reversal potential in a moment. And again, we can calculate this by simply knowing the ionic concentrations. We can manipulate and we can determine the extracellular ionic concentration. We can measure the intracellular concentration. By simply knowing that, we can plug this into this particular formula. How good are you guys at math? Oh, really good. Well, that's good. So this is an equation. Usually, to be honest, I don't like having you remember equations, because I'm not so great at remembering equations either, but knowing how to use these equations will become important. And this is the Nernst equation that all of you will probably remember from your third year class. We're going to go through this in a slightly different way. Most of these are familiar terms to you in terms of the charge of the diffusible ion, the universal gas constant, the temperature, Faraday's constant, etc. When we start going in and we start plugging in different values for this, one of the things that we do is we cheat just a little bit when we start plugging in values for the universal gas constant. We won't do that yet for the charge of the diffusible ion. When we go through and we do all of that, we get this overall value of about 2.3 log 10. At 27 degrees though, if we replace this temperature with 27 degrees, we can actually cheat because that becomes 300 Kelvin. So absolute temperature 273 plus 27 equals 300. When we go and do that, this equation simplifies dramatically to this, 60 millivolts. You don't have to go and do all of these calculations. So by simplifying it to 27 degrees, it allows us to use that temperature factor to 300, which allows us to cancel things out. And this gives us 60 millivolts over the charge of the ion with the log of the extracellular and intracellular concentrations. Okay. Now, this again becomes important, and I'll take you through a couple of these things in a moment. So if we go in and we start doing this, let's say we know that the extracellular concentration of potassium in our particular preparation is 1 millimolar outside the cell, and on the opposite side of the phospholipid bilayer, we have 10 millimolar potassium. If we plug this in, and we assume that it's at 27 degrees, if we plug this in, we get this overall ratio of 1 over 10, or 0.1. So you guys are good at math. What is the log of 0.1? Sorry, it's -1. It's exactly right. So if we were to go back and plot this now on this IV curve, and this is an IV curve, you'll have to become familiar with it. We'll go through this one with potassium to begin with, and then we'll go through some others a little bit later on. This is an IV curve. The IV curve is always drawn this way. By convention, it's always drawn this way. If you are asked, and it typically is something that I ask on your midterm, to draw out the IV function for a particular ion, you will always put on the x-axis the membrane potential, and on the y-axis you will always put the current. By convention, we talk about positive ions moving into and out of the cell. When we talked about potassium, potassium has a single charge, it's positive, and so we can use this as convention. So at the equilibrium potential, at this particular concentration, this would be representative of the reversal potential. So there is no net movement. There's no net movement of potassium. Does that mean that potassium is not moving at all? Is the channel open? Channel is open, ions are moving, but there's no net movement. There's not a buildup outside the cell in excess or inside the cell in excess, but potassium is still moving, but there's no net charge associated with it, which makes sense. There's no current. So if there was a current, it would either be up here or down here, and in fact, there isn't. It's at 0. No net movement, 0 current, perfect. And we're at this -60 reversal potential. Why do we call it a reversal potential? Because this is the potential if, when we start to inject positive charge into the cell, and we start to make the membrane potential more and more positive, one of the things that we will see is that potassium no longer will be in that equilibrium state, because we are now putting more positive charge inside the cell. And as a result, the electrochemical forces do not balance anymore, and there has to be a net movement of potassium. With a more positive membrane potential, only due to potassium, and we're only looking at one ion at a time at this point, just one. So if the only thing that this was permeable to is potassium, and it's only potassium, the only thing that we're concerned with is potassium. With a more positive membrane potential, the ions will have to start moving outside of the cell. Okay? So if you were to go back and plot this, what you would see, this is in the positive direction. The membrane potential starts becoming more positive, so less negative, in other words, it's getting closer to zero. And because it is now moving out of the cell, it would be in this upward direction. Okay? Does that make sense to everyone? So if you do the exact opposite and you start to inject negative charge into the cell, and by injecting negative charge into the cell, the difference, the voltage difference, remember potential difference, across the cell becomes more and more negative. If that happens, what do you think will occur? Perfect. So first, the potassium the potassium ions no longer in electrochemical equilibrium. There has to be a net movement of potassium. And again, with the more negative VM, in order to try to get that back to an equilibrium state, there has to be movement of ions into the cell, which is exactly what you would see. You would see movement into the cell. So one of the things that you would see here, if you continue to plot this out, this would be an IV curve for a leak potassium channel. There are two things that I want you to remember from this. One, it's a leak potassium channel. Do you guys have any idea what that means? Leak potassium channel. Yeah. It's open. That's right. It's not gated by anything in particular. Did you have something else to add? It doesn't really saturate. That's right. It depends a lot on the electrochemical gradient that's available to it. So when we talk about a reversal potential, the reversal potential is here. And you can see that it reverses from flowing into the cell for positive potassium flowing into the cell at the reversal potential, which is the equilibrium potential, no net movement of ions. It reverses in the opposite direction when you start injecting positive charge. Does that make sense to everyone? So knowing where it crosses when there's no net flow becomes important, because if you don't know anything else about a cell, you can measure by changing some of the ionic concentrations, you can measure the reversal potential for a particular ion. And we'll see how that comes into play later on when we start going into G protein coupled receptors a little bit later on. So this concept of knowing when there's no net flow of ions becomes important. Being able to identify the equilibrium potential becomes important. Is that okay for everyone? So again, just to reiterate this, with more positive charges being injected, which means that there's a more depolarized membrane potential, potassiums will have to move out of the cell, and the resulting loss of this positive charge tends to drive the membrane potential back toward that equilibrium that we looked at before. Again, we manipulate the system, but this is what it's trying to return back to. And then the exact opposite occurs. In contrast, if you start injecting more negative current into the cell, the second scenario that we took a look at, it would hyperpolarize or reduce or make more negative the membrane potential, and potassium ions will have to move into the cell to compensate to try to move it back to that equilibrium potential. Again, that resulting gain of those positive charges inside relative to the outside, remember we're always measuring inside relative to the outside, drives that membrane potential back toward the equilibrium potential for potassium. Ions are always trying to get back to that zero state or that net state. And so calculating the amount of current that gets generated between the movement of these ions really depends on a couple of things. We need to know the difference between the membrane potential as well as the equilibrium potential for a particular ion. And by knowing that, we can go back and calculate the movement or the current associated with that ion. So let me ask you this. I don't know if it's in your notes or not, but don't look if it is in your notes. So if we had this scenario, and we had this scenario where we had 10 millimolar sodium outside, 1 millimolar sodium inside, and the only thing that was available to us is this potassium channel that is open, and let's say it's somewhat selective. Does this apply? Can we calculate it for sodium for this particular patch of membrane? It would work for potassium really well because this is a potassium channel with a pore that's selected for it. You can only do this equilibrium potential if it can diffuse through the channel. So if that potassium channel did allow for sodium to flow through, yes, but in most cases it's selective. And these lead channels tend to be selective as well. We can only use that value, and it's really important, we can only calculate an equilibrium potential for that ion if it can actually diffuse through that channel. In this case, in that previous case, it can't. And so there would not be an opportunity to be able to look at the equilibrium potential, even though there's a difference in the concentration gradient. Now let's assume that there is a channel that exists for sodium to move down its concentration gradient. We have more sodium outside. And in this little microdomain, if we have this overall Nernst equation and we plug in these numbers, again, what temperature do we have to assume that this is occurring at? 27 degrees makes life a lot easier. We can use this particular equation. And so what is the log of 1? Oh, sorry, log of 10. You're right. You're right. So what's the log of 10? 1. Perfect. So that would mean that if we did this calculation and we did this for this particular patch of channel, we would be able to see that the reversal potential or the equilibrium potential, it's the same thing, would be 60, and here it is at 60. At 60, the reversal potential, we would see that there is no net current, and again, on this y-axis, it's at 0, which means that there's no net movement of sodium into and out of the cell through that open channel. So again, being able to calculate this, it becomes really important if we start manipulating this process. For all of these different lead channels, and again, I'll draw your attention to the fact that this is not a gated sodium channel. If it's a gated channel, it looks very different. A lead channel has this very linear-like response. You will see this linear response when you go into the tutorial and do the computer simulations. You'll be able to see the difference between a lead channel, which is always open and is always dependent on the concentration differences available to it, versus a gated channel, which is what we'll talk about in the next lecture. So we haven't looked at this particular scenario yet. What happens if we look at anions? Is it any different? In reality, it's a little different, but not overly so. So let's assume that we have a difference in concentration, which allows for the net movement of ions into the cell in this little patch, in this microdomain. Again, 10 to 1, just to make our lives a little bit more easy. And again, at about 27 degrees. And let's assume that this channel is open. So the convention is a little bit different here. Remember, when we talked about these conventions at the beginning, we are looking at the movement of net positive charges, right? It was one of the conventions that we looked at. Chloride is a negative anion, and so we do exactly the same thing. We go back and we calculate using Nernst the difference here, again being 10 over 1, log 10 over 1, or log 10 is 1. So we should have 60, but the charge being minus 1 makes this minus 60. So on this IB curve, we have it here at minus 60 because of the charge. The convention being here, it's a little different. Here, when we start injecting charge, chloride is going to start flowing inward. This represents the inward movement of an anion, a negatively charged ion. And here it represents chloride flowing out. So it's a little bit different, but overall it's exactly the same idea or process. How many of you are lost at this point? Not too many, or kind of lost, but you think you can work through it if you spend some time on it? I'm hoping. Would you like me to ruin your weekend for you or ruin your Friday for you? Neither. Okay, good. I like the way physiologists think, very outside the box. So I would like you to be familiar with being able to do and draw these different types of curves. If it's okay with you, I'm going to give you some problem sets for you to work on. You can share like your ideas and whatever else, wherever you want. They're not too involved. And as long as you can do them, you'll be able to do the questions that you'll get on your midterm. So whether or not it ruins your weekend for you or not, I don't know. As physiologists, maybe that turns you on. Again, I don't know. So we'll see, but I'll make that available to you and I'll probably give that to you before or during the next class. Is that, yeah, did you have a question? Yes, you do. Yeah, I can't, I don't know. Sometimes I get really confused by log base 10 as well. So if I can't do the calculation, you know, I don't think it's all that fair for you to be able to do that calculation in your head. But most of them will be really simplified, so you wouldn't need one if you got stuck. So there are many, many different ion channels. It's not just one, and you all know that. It's not just one channel. They're not all lead channels either. So we're getting to how we get the resting membrane potential, because we know that the resting membrane potential isn't due to just one particular ion. There are many different ion channels in these neurons at rest, some of which are open at rest, which allow for the free movement down this concentration gradient that we just talked about. Some of those channels are not open at rest. When the neuron is at rest, it's not firing, it's not doing anything else. Some of those ion channels are not at rest, and the membrane potential has to change before they open, or a neurotransmitter has to bind. Can you give me any examples of either one where these channels are closed at rest, but require either a change in membrane potential or a neurotransmitter to bind? Any type of receptor or ion channel that you know of. So voltage-gated potassium channels that when the membrane potential changes across the phospholipid bilayer, it causes a conformational change in the pore protein, which allows it to open. Great. That's the first category, and we'll talk about that in the next few lectures. How about a neurotransmitter binding causing a channel to open? Anything that you remember from your GABA would work? Sure, and it would open a chloride channel. Anything else? Nicotinic receptors? Okay, I'll go for nicotinic. Glutamate, okay, so glutamate receptors like AMPA or NMDA, all of these are neurotransmitter binding type, and we'll actually cover all of those in the upcoming lectures as well. So when we're looking at all of this, when we're looking at the membrane potential for a particular neuron, we have to calculate this based on all of the different ionic equilibrium potentials, as well as the ionic permeabilities. So this gets into the derivation of the Goldman equation, which I think you all cover in your third year, so I won't go through all of that as well. Again, I'm not going to be asking you to derive this from first principles or anything, but to be familiar with how we go about using the Goldman equation, both in tutorial as well as in the next few lectures. So all of this relates to permeability. Is the channel actually open? Is there permeability for that particular ion that we're talking about? For example, for potassium, is the potassium channel open? Is the sodium channel open at rest? Or is the chloride channel open at rest? And again, that one convention that we have here, because it's minus log A over B, when we invert this, we can simply have in over out instead of out over in. And it's just related to the minus log function, where we can switch the B over A, intracellular to extracellular. So this goes back to that driving force that we talked about. You will need to understand, by the way, that one equation that we talked about with the equilibrium potential and the driving force, the difference between the membrane potential and the equilibrium potential. You will need to know that a lot in the upcoming weeks. Okay, and this gets back into what we'll revisit in your tutorial next Friday. You will go through that exercise next Friday, as well as what you'll need to know for your midterm. But we need to know all of this because we can measure it, and it helps us to understand how the neuron is normally supposed to function. So this gets into a different version of the Goldman equation. Because we're looking at permeability, a similar concept to that is conductance. They're slightly different, but overall we can change conductance for permeability. So when we go back and we replace permeability P with the conductance G, along with the reversal potentials, we can rewrite the Nernst equation in this form. So the Goldman equation for any particular ion can also be used, and you'll have to be able to apply that as well. So it could be for any one of these. If all of these are closed, if sodium is closed, if potassium chloride is closed and only potassium is open, then the membrane potential becomes due only to the conductance toward the equilibrium potential for potassium. Okay, and we can measure all of those, and it tells us at rest which of these ions are contributing to the resting membrane potential. And I think most of you know the answer. Well, what does contribute most to the resting membrane potential? So most of it is potassium. But do you actually know how they calculated that? How did they actually figure that out? You learned that through third-year physiology. But how did the original physiologists go about calculating that and figuring out that it's really potassium that contributes the most to the resting membrane potential? Do you have any ideas? Yes. Okay, so the original experiments were done in the 1960s. Okay, so that's not bad. So tetrodotoxin is a voltage-dependent sodium channel blocker. Might work here. You might be able to block read channels as well. But this is what we're going to actually begin with in the next lecture. So it's one thing to understand the net movement of ions, but I'm going back to first principles. I'm going to try to show you how the actual original scientists tried to figure out what causes this neuron. When we stick an electrode in this neuron, we always consistently measure -65. When we do the calculations, that means it must be potassium. How did they actually go about proving to everyone else that it's really potassium conductances, the movement of potassium at rest, that accounts for this -65? And this is what we're going to be talking about, these leak conductances, in the next lecture. So we have a couple of minutes. Do you have any questions, or more importantly, do you have any suggestions on what I can do to help you either do well on the midterm or understand the material better? Any ideas? Suggestions? Nada? No? You'll think about it, and I'll leave that for you for homework, and you'll let me know in Friday's class. And I think Friday is a 2-hour class, if I'm not mistaken. We'll try to make it about an hour and a half, and we'll do some problem sets toward the end, if that's okay.